So this next section, we're going to talk about points of concurrency and circumcenters and in-centers. So first, I'd like you to copy down the vocab so you can pause it to copy it down. I'll go ahead and read through it real quick. So concurrent means when three or more lines intersect at one point, and a point of concurrency is the point where the three lines intersect. So we're going to have a circumcenter of a triangle, and that is the point of currency of the perpendicular bisectors of a triangle, which we looked at last section. And then the in-center of a triangle is the point of concurrency of the angle bisectors of a triangle, which again, we looked at those last section. So one of the theorems we get is concurrency of perpendicular bisectors theorem. So that just says that the perpendicular bisectors of the side of a triangle are concurrent at a point equidistant from the vertices. So wherever that point is, it's going to be equidistant from the vertices. So here's the diagram. And so what that means in words is that the perpendicular bisectors PX, PY, and PZ are concurrent at the point P. So that's where all the perpendicular bisectors meet. And what that means is that PA is going to be equal to PB, which is going to also be equal to PC. When we're talking about points of concurrency of the perpendicular bisectors, that is the circumcenter of the triangles we just went over. So when you're talking about that, you say that the circle is circumscribed about the triangle. Then there are three different ways that the circumcenter could reach. So you could have an acute triangle. The circumcenter would be inside the triangle. For a right triangle, it could be on the triangle. And then for an obtuse one, it would be outside of the triangle. So our first example here says, what are the coordinates of the circumcenter of the triangle with vertices 2, 7, 10, 7, and 10, 3? So I have those plotted. So what we're going to try to do is we find the intersection of two of the points of the perpendicular bisectors. So our easiest lines to get perpendicular are AB and BC. So we're trying to figure out the perpendicular bisector. So first we're going to have to figure out bisector is going to be the midpoint of those 2 points. And then perpendicular would be our opposite reciprocal slope. So for AB, we're going to find the midpoint. So the midpoint, we're going to take our x plus x divided by 2 and y plus y divided by 2. So we're going to have 2 plus 10 divided by 2 and 7 plus 7 divided by 2. So that's going to equal 6, 7 for the midpoint. And then our slope for AB, it's a horizontal line, so our slope is 0. So we know that our perpendicular slope is going to be an undefined line, which will be a vertical line. So we're going to have the point at 6, 7, and that's, again, going to cut B in half, AB in half, and then if we draw that line through, that's going to make a right angle there. Now the next one, again, to be perpendicular to easiest is BC, so we're going to do the same thing. We're going to find the midpoint of BC. So we're going to take 10 plus 10 divided by 2 and 3 plus 7 divided by 2. And that's going to give us 10, 5 for the midpoint. And again, we're going to do our slope, which is undefined for this one. So the perpendicular slope would be 0. So I'm going to plot 10, 5. And again, that's going to cut in half BC. And then we're going to draw a dotted line there that would also be perpendicular to BC. So then right here, we can tell where our point of concurrency is going to be. So it's going to be right here where those two meet on AC, and that is at point 6, 5. So then 6, 5 is our answer. So next we're going to talk about concurrency of angle bisectors. So similar concept, except for now we're looking at the angle bisectors instead of the perpendicular bisectors. So the bisectors of the angles of the triangle are concurrent at a point that's equidistant from the sides of the triangle. So in the diagram here, we have that AB, BP, and CP are the angle bisectors, and they're concurrent at P, meaning that they all meet at P. And so that's going to make px equal to py and equal to pz. So that is called the incenter of a triangle. So that's where they all meet at. And so when you're talking about that with a circle, you say that P is the center of the circle that is inscribed in the triangle. And then we're going to look at an example here. So they give us that QN is 5x plus 36 and QM is 2x plus 51, and we need to find QO. Well, we know from the theorem we just read that QN has to equal QM, and which also equals QO. So we're just going to set them equal to each other and find x first. So we're going to take 5x plus 36 equals 2x plus 51. So we get 3x equals 15. So x equals 5. And now it doesn't matter which one we plug back into because they're all equal. So we're going to have 2 times 5. So I'm plugging back into QM. So plus 51 equals 61. So that equals QO as well, which also equals QM, which also equals QN. Now the next question for part B says, is it possible for QP to equal 50? So if we look at QP, that's that side right there. Okay. Now we know that this is not going to be possible because we just said that QM is going to be 61. So when we're talking about the incenter, that has to be the shortest distance to the sides of the triangle. So therefore, QN and QM and QO, those all have to be the shortest distance from Q to the side, KL. Just as QM would have to be the shortest distance to JL, and QO would have to be the shortest distance from JK. So therefore, we can say that QP would have to be greater than QN, meaning that QP would have to be greater than 61, so there's no way that it could be 50.